All right, our first speaker in this third session is Nee Doan, who's joined us this summer from Pomona College. Nee's been working this summer with Julia, and she's going to tell us about their project together, Wavefront Metrology of Volume Phase Holographic Grating Prototypes for MIRMOS.
Thank you, Wen, for that introduction. Hello, everybody. This summer, I've built a Wavefront metrology setup and used it to test some gratings, and I'm super excited to tell you about my work today. So to start, I want to introduce you to the scientific motivation for my project, which is MIRMOS. MIRMOS is an innovative spectrograph that's currently being designed and developed for the Magellan telescopes at Las Campanas Observatory in Chile. MIRMOS will operate in the near-infrared regime, and it will observe many interesting science cases. But the key ones are tracing faint galaxies across cosmic time, probing the kinematics of the circumgalactic medium, and also understanding the molecular content of exoplanet atmospheres. So even though these are very different science cases, what unites them is the common desire to maximize optical throughput, meaning to maximize the amount of light that actually passes through the instrument to the detector, while minimizing scatter, which might degrade the signal-to-noise ratio of the observed spectra. So there are many ways that MIRMOS is designed to achieve these two goals, but one of these ways is by using volume phase holographic gratings, or VPH gratings. And so VPH gratings are the focus of my talk today. So what are VPH gratings? These belong to the broad category of diffraction gratings. So they are dispersive elements. They split light into a rainbow. Traditionally, a diffraction grating might be a surface relief grating, also commonly known as a rolled grating. This rolled grating has grooves that are etched onto its surface. And so these surface grooves reflect the light of different wavelengths into different directions, and therefore splitting the light into a spectrum. In contrast, VPH gratings work in transmission. Structurally, you can think of these VPH gratings as peanut butter and jelly sandwiches. So the middle jelly layer is a dichromated gelatin film that has a periodic pattern of alternating high and low refractive index regions. And it is this periodic variation in the refractive index that is responsible for the dispersion of light. This jelly layer is sandwiched between two pieces of glass that provide thermal and mechanical insulation. So there are many advantages to using VPH gratings. Some of them are that VPH gratings offer very high optical throughput. They also don't have surface features, so they scatter very little light. And gratings that work in transmission are mechanically compatible with MIRMOS's layout. In my project specifically, I'm looking at one aspect of VPH gratings, and that is their image quality. So here, I focus on 4 VPH grating prototypes that were fabricated for the MIRMOS project by a group in Italy called INAF. And these grating prototypes come in 4 flavors corresponding to the 4 infrared spectral bands. So we have K, H, J, and Y. And I built a Wavefront metrology setup in order to validate these grating prototypes' image quality performance by measuring the wavefront error and then comparing our measurements to the vendor's measurements. So what is wavefront error? Whenever light passes through an optic, such as a VPH grating, its wavefront will get aberrated or distorted due to the imperfections in the optic. This deviation of the actual wavefront from the ideal wavefront is expressed as wavefront error. And why do we care about wavefront error? Because wavefront error directly impacts the image quality. Specifically, it has an impact on spectral resolution, on signal-to-noise ratio, and on contrast. So by measuring the wavefront error associated with these 4 VPH grating prototypes, we want to quantify how much they will degrade the image quality of MIRMOS. So now moving on to the experiment setup that we built to test these 4 VPH grating prototypes. Remember that wavefront error is the difference between the actual wavefront and the reference wavefront. In my experiment, I make 2 measurements, one of the reference wavefront and the other of the actual wavefront. So we start with a laser diode that sends light down and then to the right, so it passes through a bunch of optics. But after this final element, which is a collimating lens, the output beam is a collimated beam of light, meaning that all of the rays of light are parallel as the beam propagates. So this collimated beam bounces off the surface of a flat return mirror and then travels to the left, where it's focused to the focal plane of a wavefront sensor. So this is how we make a measurement of the reference wavefront. And to make a measurement of the actual wavefront, we just insert the VPH grating in between this collimating lens and the return mirror. So here is a quick summary of the two measurements I'm making. And this is a picture of the actual experiment setup as it's living on the optical bench. So now, how do we actually quantify wavefront error? We use a detector called a Shag-Hartmann wavefront sensor in order to accomplish this goal. A Shag-Hartmann wavefront sensor is a 2D array of very, very tiny lenses. Each of these lenses focuses one part of the incoming wavefront to a spot on the focal plane of the sensor, so that if you have a perfectly flat wavefront incident on the sensor, the spot grid that forms at the sensor's focal plane is going to be perfectly symmetric. However, it's a different story if the incoming beam has some aberrations, because then each of these spots is going to have its centroid deviating from its ideal location, because these local spot centroids are very sensitive to the angles or the tilts of the incident wavefront. So the Shag-Hartmann wavefront sensor measures all these spot centroid deviations and uses these data to reconstruct the wavefront and spit out a value for the wavefront error, as well as it tells you what types of aberrations there are in your system. So with my wavefront metrology setup, I performed some early measurements of the wavefront error of the VPH grating prototypes, and here are some early results. So spoiler, there's some good news and there's some bad news. The good news is that our early wavefront error results are in qualitative agreement with the vendor's measurements. So here I'm showing two wavefront maps of the Y-band grating prototype, and wavefront error is expressed, is color mapped based on this vertical color scale bar. So to the left, we have the wavefront map of the Y grating made by the vendor, and to the right, we have a wavefront map made by me using our setup. So qualitatively, you might notice this red feature that runs vertically across the pupils of the two wavefront maps. And so this red feature is indicative of large astigmatism, and astigmatism is an aberration that occurs when the surface of an optic is curved more in one direction than the other. So this agrees with what the vendor tells us about the Y grating, because this astigmatism is supposed to be indicative of directional bending that was supposed to be introduced during the gluing process. So the fact that we're seeing the same feature in a wavefront map is really encouraging. However, there are some problems that remain. The first one is that we're not seeing the full clear aperture due to our setup limitations. So in our setup, we use a 30mm circular pupil to retrieve the wavefront map of the Y grating. However, the pupil that was used by the vendor is actually 35mm in diameter, so it's larger. So now you might be wondering, why don't we just use a 35mm circular pupil? Well, if we did that, we would be incorrectly including all these dark pixels that don't belong to the grating's clear aperture. And the reason why is that in our setup, the VPH grating is tilted to about 30 degrees in order to produce the optimal diffraction pattern, but that geometrically limits how much of the clear aperture we're actually seeing with the sensor. So we're forced to live with a smaller pupil. But so a smaller pupil is sampling this central region of the clear aperture, which has a higher wavefront error concentration than the average wavefront error, and that might have inflated our wavefront error measurements, and that might partially explain the factor of two difference that we're seeing in our measurement and the vendor's measurement. Another problem that we're running into is that our wavefront error measurements show unwanted time-dependent variations, which is weird because during the experiment, we're not doing anything to perturb the VPH grating prototypes. So being shown here is a plot of the RMS wavefront error tracked over the course of 45 minutes. And as you can see, there are a lot of like seemingly random variations over time. We've recently discovered that these time variations in the RMS wavefront error seem to have something to do with time variations in image saturation. So here's the same plot of the RMS wavefront error and an additional plot of image saturation also tracked during the same period of time. So if we just black out these regions that correspond to the times when the laser intensity was reset in between measurements, then we can see some interesting patterns or phenomena. So for example, in the region here that I'm highlighting in red, This is when saturation spontaneously dropped below 80% to about 50% before climbing up again. And so during this time, RMS wavefront error spontaneously doubled its value before falling to its initial value. Or another example is this region in blue where saturation becomes really noisy, and during that time, the RMS wavefront error just randomly resets itself to a new value that is more than double the initial value. And as you can see, it never quite recovers after that reset. So this is something that we don't fully understand yet, and it's weird because theoretically we don't expect wavefront error to be sensitive to any changes in the beam intensity, which is related to image saturation. However, what happens is that the software needs to keep saturation high from about 90 to 98%, and also saturation must be kept stable over time in order for the software to properly calculate wavefront parameters. So the origin of this time variable phenomenon is something that we're still investigating. So to offer some final takeaways from my presentation, VPH gratings are currently being selected for MIRMOS based on their unique capabilities for maximizing optical throughput while minimizing scatter. In my project, we built a wavefront metrology setup to validate the image quality performance of 4 VPH grating prototypes that were fabricated for MIRMOS. And what we found so far is that our early measurements are in qualitative agreement with the vendor's measurements. However, there might be some systematic issues that we have yet to properly diagnose. So that is the end of my presentation. Thank you for tuning in, and I would be happy to take questions.
Okay, very nice. Any questions for me? Izzy?
Great talk. So do you know what the difference is between your setup and the vendors where they're able to capture the full 35mm people?
Yes. So the vendor used a Zygo interferometer. So it's an interferometric setup, and I didn't have the time to actually go into the details of that setup. So that's something that I don't understand. And but according to their documentation, they did use 35mm circular pupil. So the square aperture of these VPH gratings are 35 by 35mm. So they're able to use a 35mm circular pupil to inscribe that full clear aperture. But we're not seeing the same like full clear aperture in our setup. So I don't have like an apple to apple comparison, but according to their documentation, this is what they were able to see.
Other questions for me? Allison?
For this talk, I have questions. One of the second one. I wonder always about instrumentation, if it broke anything one way. And then the second question I have is, you're doing your experiment at with temperature, right? And then you're not super cold. You expect that the measurement to temperature well.
Thank you for your two questions. So the first one, I did not break anything, but there were many times when it almost broke something. It's a really intricate setup, and some of the maps are not very secure, and like there are many ways that you can like apply pressure to something and like a screw would like fall off. So I can go like on and on about it, but the second question, I have a slide for this. So it's true that MIRMOS, because it's a near-infrared instrument, it's gonna operate at cryogenic temperatures. The purpose for my project is to make measurements of the wavefront error at ambient temperatures, because we want to validate the measurements made by the vendor, and those measurements were made at ambient temperatures. So that's what we want to compare. The next step for my project, or whoever is going to continue my project, is to do thermal cycling tests. So because VPH gratings are composed of a gelatin layer that's bonded to these two pieces of glass by an epoxy. These materials have different coefficients of thermal expansion. So when we bring them to like a cooler temperature, worry that the gelatin layer might delaminate from the glass and for the mechanical structure for the entire thing to break. So what would be interesting is to conduct these thermal cycling tests where we might dump the VPH grating into liquid nitrogen or something, and then like bring it back to room temperature, and then measure to observe whether the mechanical structure survives that thermal cycling process, and if it does, then what's the impact on wavefront error. And I don't have the quantitative predictions for that, but that's something interesting to look at. And then for the future, I know that Jared, who's like one of the instrument people here, is building a cryostat for testing the VPH gratings as well as other objects from MIRMOS at cryo conditions. But cryo setups are really complex and costly, so we don't expect to have those setups anytime soon.
Great, let's thank me again.